Welcome to the Unit 8 Test Remediation Packet. This is the guided practice. We're going to walk you through some of the categories that you may see on the test and help prepare you for the independent practice. In this case, it says the wave characteristics. This is examine the wave below, classify the wave, label the terms, and describe how you can change each of the terms above. So the first thing that I'll realize is because it's moving this way and it's oscillating this way, it has to be a transverse wave. So since it's a transverse wave, I can find the amplitude by looking at this equilibrium line. The equilibrium line is the point that's exactly halfway between the crest and the trough, and the distance from that equilibrium line to either a crest or a trough represents the amplitude. So you can measure the amplitude as the equilibrium to the top or equilibrium to the bottom. The amplitude is the same number in either case. We've already labeled the crest and the trough. And then the wavelength represents the distance between identical points on a wave. So the easiest thing to do is say crest to crest. That represents one wavelength. But you should also be able to identify it in the middle of a wave to the middle of another wave. So this right here represents one wavelength as well. Okay, and describe how you can change each of the terms above. If you have this and you're somehow making this, you need to increase the energy, and that'll change the amplitude. Whenever you increase the energy, it also changes the position of the crest and the trough. And then finally, for the wavelength, it has to do with if you make your sweeping motion faster, it will actually decrease the wavelength of the wave, generally speaking, as long as you have a consistent velocity on a wave, on a string. So the next one you should be able to know is longitudinal. You should be able to say why. You should recognize that there is no amplitude. You should be able to identify that as a compression. This is a rarefaction. And you should be able to say a wavelength is a compression and a rarefaction together. It says describe how you can change these. Same thing, you're going to put more energy in. Whenever you put more energy in, it's going to affect the wavelength a little bit. So it's really hard to change much with compression waves unless you can change the medium in which it's traveling. Finally, you should be able to recognize this as a pulse. A pulse is very similar to a transverse wave. So this right here represents the amplitude. Okay, it doesn't have a compression, it doesn't have a rarefaction, and it doesn't really have a wavelength because it's only a part of a wave. Okay, now it asks me to calculate the distance. A radio wave will travel if it has a speed of 3 times 10 to the 8th and travels for 10 years. So the first thing that you should realize is that it tells me the speed of the wave, so I know the velocity is 3 times 10 to the 8th, and that's in meters per second. So in order to use that number, I need to have my time term, and that time needs to be in seconds as well. Right now it's in 10 years, and that's not going to work for me. So I could go years to days, days to hours, hours to minutes, minutes to seconds, or if you know that in 1 year there is 31,557,000 seconds. Okay, when you take this and you multiply it out, you get 315,570,000 seconds. Okay, so at this point, you have a velocity, you have a time, it is a constant velocity, and so because of that, you can use the equation v equals d over t, or 3 times 10 to the 8th equals d over 315,570,000. Multiply both sides by 315,570,000, and you get a distance of about 5 meters per second. Excuse me. A distance, it's going to be a whole lot more than that, 9.47 times 10 to the 16th meters. Is a really big number. Okay, now it says calculate the velocity of a wave on a string that travels down one length and back in 4 seconds. So one thing you need to realize is that the wave travels this way for 10 meters and then this way for 10 meters. So if you look at the wave has actually traveled a distance of 20 meters. Okay, now you should be able to figure out that the velocity of the wave is about 5 meters per second. Okay, so 5 meters per second. And then finally it asks you to calculate the time of a sound wave traveling that. You should be able to figure out that it's about 0.3 seconds. We'll round it up a little bit. Okay, and the next one Another calculation says scientists discover a new N wave they believe to be part of the electromagnetic spectrum. It says the wave has a frequency of this and a wavelength of that. Is it part of the electromagnetic spectrum? So what you should realize is that all electromagnetic spectrum waves travel at 3 times 10 to the 8th meters per second. So if I can figure out that these waves have a velocity of 3 times 10 to the 8th meters per second, it's a good indication that they're probably going to be electromagnetic spectrum waves. So we test it, we say velocity is equal to wavelength times frequency. In this case, it gives me the frequency as being 2.5 times 10 to the 18th hertz, and then finally I get a wavelength of 8 times 10 to the minus 11th. When I plug those numbers in, I get 8 times 10 to the negative 11th times 2.5 times 10 to the 18th, and I would multiply those out. And when I multiply those out, I'm going to get actually kind of a strange number. I don't actually even have to multiply it out really, because 8 times 2.5, if you were to multiply that out, is not going to be, it's going to end up being 2. It's actually going to be like 20, but whenever you multiply it out, it's going to be 2 times 10 to the something. Well, 2 times 10 to the something cannot equal 3 times 10 to the something. So because of that, this is not a true statement. Therefore, this wave cannot be classified as an electromagnetic wave. Okay, on the next one, you should be able to look at this. The one thing that you need to be careful about is you have 450 nanometers. This right here is in meters per second. So you're going to have to convert nanometers to meters. And remember, that's 1 nanometer is 1 times 10 to the minus 9th meters. Okay, whenever you do this, you should be able to get it to 6.67 times 10 to the 14th hertz. Okay, and then finally it says calculate the velocity of an ocean wave. Okay, so whenever you do this, you should end up getting a velocity of about 30 meters per second. Okay, next we just have one that we're looking at, a standing wave. So it says draw the second harmonic that is generated at 20 hertz. So you should be able to say this right here represents one harmonic, two harmonics. So there's two harmonics because there's two bumps right here. So I would say that this right here represents an antinode, and this right here represents the amplitude, which is the same distance. So you have the amplitude, you have the antinode. These three things right here, and there are three, are nodes. Okay, so I've got two antinodes. I've got the amplitude, I've got the node. The wavelength represents any two antinodes, so that right there represents the wavelength. And then it says to calculate the fundamental frequency. So this whole thing happens at 20 hertz. And what I can say is that the frequency of some harmonic, I don't know, is equal to that harmonic number times what's called the fundamental frequency. So in this case, I have the second harmonic at 20 hertz. So because of that, I can figure out what the fundamental frequency is, and I can predict that it's going to be at 10 meters per second. Excuse me, at 10 hertz. Okay, whenever I look at 10 hertz, that is where I would look for the first harmonic, which would be something that looks like this, just one bump. Okay, now it says if the string is 5 meters long, what is the speed of the wave on the string? So in this case, I'm going to discount my fundamental frequency. I'm going to go back to my original. So I have 20 hertz, and then I have that this string, which is one wavelength, is 5 meters. So if you look, I have a velocity, wavelength times the frequency. The wavelength is 5, only because a wavelength is two harmonics and it takes up the whole string. And I have the frequency is 20. Whenever I do that, it's 100 meters per second. Finally, it says match the wave phenomenon with a real world example. Reflection is an example of radar. Okay, refraction is an example of microscopes. Okay, diffraction is an example of hearing around the corner, and resonance is used in musical instruments that magnify the sound. So go ahead and try the independent practice, and if you have any questions, make sure you talk to your teacher before your retest.